Marcos and get him for attendance. All right, so Alberta, good to go. Okay. All right, if you guys see somebody else pop in, please let me know. All right, there's Luis. All right. So, last class we went through and we talked about the different types of energy, and I gave you guys a pretty comprehensive overview. There is a video that I did post, or I did a live stream of during first block yesterday, so February 3rd, or yeah, February 3rd, that went over the concepts, and you guys can go back and watch that if you need a refresher. So what we're going to do today, it's going to be a pretty quick lesson. I'm going to give you guys some examples of how to figure out the kinetic energy, gravitational potential energy, and elastic energy. Cool. So, just as a refresher, the equations that we have for energy, the first one that I'm going to show you is kinetic. So kinetic energy is going to be 1/2 times the mass times the velocity squared. Okay. So that's the first equation. The second one is going to be gravitational potential energy. So I have a subscript of grav for gravity. And then I have the U that represents potential energy. And that is going to be simply mass times gravity times the height of the object from the ground. And then lastly, we have U elastic. And that is going to look really similar to the kinematic equation, or sorry, the kinetic equation. But it's going to have some different variables in here. So, before we get too far, we've got mass, velocity, height, acceleration due to gravity, and then these two are going to be a little interesting. So the first one, this is what we call the spring constant. And that is going to have units of newtons over meter. And all the spring constant represents is, somebody else come in? No. All the spring constant represents is the amount of force required to stretch or compress a spring the distance of 1 meter. That's all it means. So if I have a high value for my spring constant, that's going to tell us that we have a very stiff spring. It's going to require a lot of force to stretch that spring the distance of 1 meter. Okay? And then this here this is the displacement of the spring. So all this means is when I have a spring and I'm not applying a force to it, I'm not mushing it together and I'm stretching it out, the spring itself has a particular length. And that's what we refer to as the rest length, R-E-S-T. And if we stretch it, the amount of it being stretched, that is the displacement of the spring. So depending on how much it's stretched or compressed, that's the delta X. And I want to emphasize that the X part of this isn't necessarily dictating that it is in the X axis. It's just how we represent the displacement of the spring. Does anybody have any questions so far? Okay. So we're going to do an example of each one of these, and then I'm going to let you guys go for the day. Cool? All right. So the very first example, we're going to deal with kinetic. So with kinetic, if I just give you an example where I have a car and the car has a particular mass and it also has a velocity, I can figure out the kinetic energy of the car. So my objective is to find kinetic energy. And usually in a problem like this, I will give you the mass and I would give you the velocity. I mean, I would have to in order for you to solve it. So in this case, we're going to say that the mass is 1,000 kilograms. And the velocity, we're going to say 30 meters per second. Cool. So my objective is I need to find my kinetic energy, and I'm given the mass and I'm given the velocity. So the equation for kinetic energy if I can get a K down, is just going to be 1/2 times the mass times the velocity squared. And it's as simple as just plugging in our knowns. So I like to put the parentheses there. This isn't a worksheet or anything. No. I'm just going through an example. So what I'm going to be planning on doing is I'm going to have some practice problems that I'm going to throw together because we need some more formative grades. And I'm kind of bad at doing like having little assignments to make sure that you guys understand what you're doing. But I think I'm going to start doing that. So, like once a week, maybe twice a week, I'm going to give you guys like maybe 10 problems to do that are literally as simple as this. That way I can get some more grades for you. Sound good? Okay. Now, all I have to do is plug in what I know. So I know the mass is 1,000 kilograms. And I know the velocity is 30. Yeah, I agree. And that's why I haven't really given a lot of work for you guys, is because I know a lot of other teachers are assigning an insane amount of work. So I try to keep my lectures pretty simple, and the material that I assess you on, I'm trying to keep it as simplistic as possible. And I also don't want to overburden you guys with extra work. Okay, so if I do 0.5 times 1,000 times 30 squared, I get 450,000. Okay. Now, we don't know what the units are quite yet. So let's try to figure out what those units are. So if I know that this is the equation, and I know that the units for mass are kilograms, and the units for velocity are meters per second, I would have kilograms times meters over seconds, but the velocity is squared, so I have to also apply that to the units. So that's why I would put a square right here. Now, this is a little weird to look at. So what I'm going to do is I'm going to distribute the square to both the top and the bottom, because that's the same thing. So I would have meters squared over seconds squared. And then when I combine this, I get kilograms times meter squared over seconds squared. And we have something here that should look familiar. I didn't really emphasize it a lot when we were talking about forces, but a kilogram times a kilogram meter per second squared is a Newton. So what I'm going to do, I'll do this just to show you the intermediate. So all I did was I took one of the meters here and I just stuck it right there. So this is converted into a Newton. A kilogram times a meter over second squared. So I get a Newton times a meter. Cool. So a Newton meter, because that pops up a lot in physics, we actually call that a joule. And it's spelled Joule, not Juul. Okay. So this is going to be a joule. Now, a lot of the times there's going to be a lot of zeros. So one of the more useful units that we use when we're talking about energy is the unit of kilojoule. So we would have kJ for kilojoule or kilojoule, however you want to say it. It's the same kind of way that we deal with grams and kilograms. So kilo just means 1,000. So 1, 2, 3. So this would be the same thing as saying 450 kilojoules. And when I give you guys a problem, what I will ask, like I will explicitly ask for you to have the answer in kilojoules or in joules. So you don't have to worry about that. Cool. So the amount of kinetic energy that this car has, the one that has a mass of 1,000 kilograms and it's traveling at 30 meters per second, the kinetic energy of that vehicle is 450 kilojoules. Cool. All right. Now, the next problem is going to be gravitational potential energy. So if I've got somebody who is standing up on a ledge, and here's the ground, and this person has super long arms, and they have a ball. The ball has a mass it also has a particular height from the ground. Cool. So height, it has a mass, and my objective is I want to figure out what the gravitational potential energy is. So I'm going to claim that the mass has a value of, we'll say, 50 kilograms. And the height is, we'll say, 100 meters. Now, if I go back up my equations, U-grav is just mass times gravity times height. And remember, in my class, gravity is just going to be 10 just to keep the math easy. So we can go ahead and throw that down here. With our knowns. So we know mass, gravity, and height. So I'm going to write down the equation. So U-grav is equal to mass times gravity times height. And before I start plugging in values, I put my little placeholders to make sure my arithmetic is good. So my mass that I claimed was 50 kilograms. So I got 50 there. Gravity is 10. Again, that's just for my class. And then the height is 100. So if I add all, or not add, if I multiply all that out, I get 50 times 10, that's 500, and 500 times 100 is, anybody want to say? $50,000. Good. All right, U-grav. Okay, so let's just make sure that the units that we have, that we were given, the kilogram, the meters per second squared, let's make sure that that comes out to the Newton meter that we had before, because we want to make sure that it's in joules. So instead of plugging in the values in order to check out and make sure that the units come out correctly, we can just plug in what the units are. So we have mass times gravity times height. So the unit of mass that we were given was kilogram. That's multiplied by the acceleration due to gravity. So that's meters per second squared. And then we were given the height, and that's going to be in meters. So if I multiply all this together, a kilogram times a meter, so we get kilogram times meters squared over then the second squared. So this looks just like before. Then we can take out one of those meters, and we have kilogram times meter second squared. This gets turned into a Newton times meter, and of course the Newton meter is a joule. So we do in fact have units of joules, and we're good to go. Now, you don't have to do this every single time. As long as you have the base units, so if you have kilogram for mass, meter for the length or the height, whatever it is, and then acceleration is meters per second squared, as long as you have those proper units, then the units will come out correctly if you plug everything in at the proper spot. Cool. So this, again, is not quite, it's not necessary, but it's a good way to double check to make sure units are correct. Any questions so far? Okay. Lastly, we have elastic potential energy. So in this situation, I'm going to have a spring that is a certain length. And then I'm going to stretch this spring a certain distance. So with U elastic, or elastic potential energy, that's what we're trying to solve. The equation is U elastic equals 1/2 times the spring constant. Make sure that's lowercase. So this letter K is a lowercase k, and that is different than the kinetic energy K. All right, so there's a reason why when I do the kinetic energy, I put the little lines on it like this. This is kinetic energy. This is the spring constant. Okay, they are different. Just want to make that quick note. And then the amount that the spring is stretched squared. So that's the equation. So if I give you the spring constant of, we'll say, 100 newtons per meter. So if I wanted to stretch that 1 meter, it's going to require a force of 100 newtons. Or actually, hold on. Let's do 600. Make it a little bit stronger spring. And then we're going to say that the amount that the spring is stretched, we're going to say is 0.4 meters or 40 centimeters. So out of any of these energy problems, this problem, like this section right here, the amount that it's been stretched, might be given in centimeters. So you just need to be on the lookout for that and make sure to convert it into meters. But just for the sake of exposing you guys to this for the first time, I'm going to keep it in meters. So what that 0.4 meters represents, so here and here, the distance that it is stretched, that is the delta x. Okay? So that's what this represents here. So I'm given the value for spring constant and delta x, so I literally just plug it in. So spring constant was 600. And the amount that I stretched it was 0.4. So 0.5 times 600 times 0.4 squared. And I get a whopping 48. And that's going to be joules. Any questions about that? Okay. So what we did today was we briefly went over what the equations were for the kinetic energy, the gravitational potential energy, and the elastic potential energy. We went through an example with kinetic energy here. So we were given the mass of the vehicle we were given the velocity of the vehicle. And with those two pieces of information, we can get the kinetic energy of the vehicle. The second example was dealing with gravitational potential energy. We were given the mass, we were given the height, and then the acceleration due to gravity. That should be something that you guys should know. So I may not actually give you the value for the acceleration due to gravity in the problem because it's such an easy variable to understand and to remember. So we literally just plugged that in and we got the value there. And then we did an example with elastic potential. I emphasized that the K is different than the K for kinetic energy. So that is not the same as that. This is kinetic. This is spring constant. And then the delta X, that literally just represents how much the spring is stretched or compressed. And since I have both of those values given to me in the problem, I literally just plug in and then I get the value. Cool. So hopefully that seems extremely easy. I want to, before I let you guys go for the day, I want to kind of give you a little bit of insight about what problem I'm going to have on the assessment. So on the assessment, it's going to look like this. So I'm going to have a box and it's going to slide down the ramp. And so it's going to go down the ramp. It's going to slide down and then it's going to get down to the ground level and then it's going to slide without friction until it hits the spring, and then it's going to fully compress the spring and it's going to be at the instant right before it launches back up and goes back up the ramp. Okay. So that's what the scenario is. So there's going to be 3 different states or points, like snapshots of this whole scenario that I'm going to be referencing. So the very first state would be when the box is up here. So this would be state 1. Okay. The second state would be when it reaches the bottom and it's traveling horizontally with no friction. So this would be state 2. And then state 3 would be when the box has compressed the spring to its full, like as much as it can, and then it's the instant right before it gets launched back up the ramp like that. Okay. So that would be state 3. So that's what the situation would be on the assessment. And in order to solve these kind of like this problem, you're gonna have to figure out what type of energy is present at each state. And let me do this. So there's gonna be a state right here where the box is right there. Then there's gonna be a state where the box is down here. So this is state 1, state 2, and then where the box has fully compressed the spring, and this would be state 3. So there's a question, or there's 3 questions that you ask at each one of those states to help determine what type of energy is present at each particular state. And this is going to be the very last thing, and then I'll let you guys go for the day. So Oops. So these are the questions that you ask yourself to figure out what energy is present. And just as a disclaimer, there's only going to be one type of energy present at each one of these states. Okay, so only one. You're going to only answer yes to the 3 questions for each one of these states, and it's going to be different. So the very first question is, does the object have a velocity? So at state 1, this is the instant right before I let it go, or the instant that I let it go. Is it moving when I start? The instant, the nanosecond after I let it go. It hasn't had enough time to start moving yet. So in that case, the answer would be no. So this, does the object have a velocity? This is referring to kinetic energy. If the answer is yes, then you do have kinetic energy. If the answer is no, you do not have kinetic energy. Cool? So this is for kinetic. The second question Grand. Is there a height from the ground? And this is referring to ugrav. So at state 1, would the object have a distance from the ground? The ground is right here. It does have a distance to the ground. So this one, it would have gravitational. It's not moving, so there would be no kinetic. And then lastly, the third question would be, is the spring compressed or stretched by the object? And this is going to be referring to U elastic. So at state 1, this is like the box is over here. So it hasn't even gotten close to the spring. So it's obvious that it's not going to be compressing it at state 1. So in that case, so for state 1, let's kind of go through and answer these questions for each state. So at state 1, is it moving? No. Is there a height from the ground? Yes. Is there a spring that's being compressed or stretched? At state 1? No. So state 1 is going to be ugrav. That's the only energy that's present. Now at state 2, that's going to be right here. Remember, that's the ground. Is the object moving at state 2? It sure is. When it gets to the bottom of the ramp, it's going to be sliding across the ground, so it has a velocity. So yes, it is moving. So we have kinetic energy. Does it have a height from the ground? It's sliding across the ground, so in this case, no. There is no gravitational potential. And it hasn't quite reached the spring yet, so obviously there's not going to be any elastic energy. So state 2 is going to be kinetic. Cool. And then lastly, at state 3, does the object have a velocity? So this is where a couple of people get tripped up. So if I've got an object and I have a spring here, and I come in and I compress the spring, and it's the instant right before it launches back. So I'm traveling. In y'all's case, I'm going. What direction am I going? It's backwards for me. So going to the right. Is that to the right for you guys? Okay. So if I'm traveling to the right, like this, and then I get to the point where I fully compress the spring, and then I'm getting ready to launch back, my direction is going to change, and then I'm going to launch back, right? So the instant that I go from going to the right, and then it goes to the left, my velocity has to be 0 in order to do the switch. So the instant that I stop moving to the right, my velocity has reached 0, and then I'm going to start moving to the left, and that's when I get launched back up the ramp. So at state 3, when I have fully compressed the spring as much as I can push it, I'm no longer traveling. My velocity is 0 at that point. So in this question, at state 3, my velocity is 0, so I do not have kinetic energy. I'm not moving. And that's only for like a split second. Is there a height from the ground? I'm still, like, of course, this is not drawn to scale and it's not perfect. So it appears like it's off the ground, but it's not supposed to. So it's still traveling, it's still touching the ground. So there is no height from the ground. And is there a spring that's being compressed or stretched? In this case, obviously, yes, there is. So at state 3, it's going to be U elastic. Cool. And notice that there's only one type of energy for each state. And what we're going to do is I'm going to give you some variables. Like I could give you the height, I could give you the mass, or whatever. And I'm going to ask you, what is a variable from this? What is a variable from that? And so on. I'm going to ask you to solve for some stuff. Cool. So Frank, there is no friction in these situations. Like we won't be dealing with friction when it comes to energy because friction is a non-conservative force. So it makes these energy problems a little bit more difficult to deal with. I mean, obviously we can figure that out, but the level of physics that we're at right now, we're going to neglect that just to make it simpler. Cool. All right. So does anybody have any questions? All right. So if you don't have any questions, I'm going to go ahead and end the live stream.